morning, students. Today we are going to discuss about the chapter structure of atom and some of its concept. We have in our previous class we have discussed about Bohr's model for hydrogen atom and its limitations as well. And its limitations is that de Broglie concept and Heisenberg uncertainty principle. Bohr's model of atom were not able to explain these two concepts. So today we are going to discuss about de Broglie concept of dual nature of matter, distinction between a particle and a wave, difference between electromagnetic waves and matter waves, and Heisenberg uncertainty principle and its significance. So let us begin. In view of the shortcomings of Bohr's model of atom, many efforts were made to develop a new model of atom which could overcome the limitations of Bohr model. So the development of new model was mainly based on the following two concepts that has been put forward. That first concept is de Broglie concept of dual nature of matter, and the second one is Heisenberg uncertainty principle. This topic we'll discuss later on today in today's class only. So we are knowing that, students, the new branch of science which was developed taking into consideration the above two concepts which I have just mentioned you is known as quantum mechanics, or we can say it wave mechanics. That is why the new model of atom is known as quantum or wave mechanical model of atom. Thus, just as Bohr model of atom was developed on the basis of Planck's quantum theory, the quantum mechanical model of an atom has been developed on the basis of quantum mechanics. It is therefore important to first understand the two concepts. So let us start with the first one, de Broglie concept of dual nature of matter. As we had already discussed in our previous classes, Einstein in 1905 suggested that light has dual nature, that is wave nature as well as particle nature. After that, Louis de Broglie, a French physicist, in 1924 advanced the idea that, like photons, all material particles such as electron, proton, atom, molecule, a piece of chalk, a piece of stone, or an iron ball, that is microscopic as well as macroscopic objects, also possessed dual character. So the wave associated with a particle is called a matter wave or de Broglie wave. We will discuss later on the differences between matter waves and electromagnetic waves. Before that, now we are knowing that the wavelength of the wave associated with any material particle was calculated by analogy with photon as follows. So suppose we are taking a case of photon. If it is assumed to have wave character, its energy can be written as E is equals to h nu according to Planck's quantum theory. And you are knowing where h is Planck's constant and nu is the frequency. Now let us consider this as equation 1. Now if the photon is supposed to have particle character, then how we can write its energy? We can write its energy in terms of E is equals to mc square, and this is according to Einstein equation. And you are knowing that here where m is the mass of photon and c is the velocity of light. So let us consider this as equation 2. Now from equation 1 and 2 we can equate, we are knowing that LHS are same, both are the expressions for energy, so we can equate the RHS side, that is h nu will be equals to mc square. But we are knowing that nu frequency is equals to speed upon wavelength. So therefore, after putting the value of frequency in this very equation, we are getting hc by lambda is equals to mc square, or wavelength we can write it as h upon mc. So de Broglie pointed out that the above equation is applicable to any material particle. The mass of the photon is replaced by the mass of the material particle, and the velocity of the photon is replaced by the velocity of the material particle, v. Thus, for any material particle like electron, we may write it as lambda will be equals to h divided by mv, or lambda will be equals to h divided by p, where mv is the momentum, that is p, of the particle. So we can call this equation de Broglie equation, where lambda is the de Broglie wavelength. So after seeing this equation, we can simply say that here wavelength is inversely proportional to the momentum. So thus the significance of de Broglie equation lies in the fact that it relates the particle character with the wave character of matter. So I hope this concept is clear to you. So let us proceed towards the significance of de Broglie equation. Let us understand it properly. As just now I have told you, although we are knowing that de Broglie equation is applicable to all material objects, but it has significance only in case of microscopic particles. This will be clear to you. Let us take one example. Suppose we are considering a ball of 0.1 kg, which is moving with a speed of 60 meter per second. Mass we have been given and speed also. Now, by using the Broglie equation, wavelength can be written as h upon mv, and we are knowing here m and v, and h is having the constant value. So after calculating it, we are getting 10 to the power minus 34 meter, the wavelength. So we can say that it is apparent that this wavelength is too small for ordinary observation because it is of 10 to the power minus 34. On the other hand, if we are considering an electron with a rest mass, which is equals to, we are knowing that mass of electron having 9.1 into 10 to the power minus 31 kg, then it will be approximate of, if we are considering that mass, then it will be minus 30, 10 to the power minus 30 kg, moving at the same speed, would have a wavelength, and that will be equals to 10 to the power minus 5 meter. If we are considering mass as 10 to the power minus 30 and having the same velocity, then we are getting the wavelength as 10 to the power minus 5 meter. And we can, if we want to write in terms of angstrom, we can write it as 10 to the power 5 angstrom, which can be, now we can say that 10 to the power 5 angstrom can be measured easily experimentally. So now, since we come across macroscopic objects in our everyday life, therefore, de Broglie relationship has no significance in everyday life. That is why we do not observe any wave nature associated with the motion of a running car or a cricket ball, etc. So I hope, using, after listening to this very example, the significance of the Broglie equation for microscopic particles, you have understood it properly. So let us proceed further. So let us discuss one question over the concept. The question is like this: if the velocity of the electron in Bohr's first orbit is 2.19 into 10 to the power 6 meter per second, you have to calculate de Broglie wavelength associated with it. It's a simple formula. By using the formula, lambda will be equals to h upon mv, and here Planck's constant, we are knowing it's having the constant value, and mass being given to us, that is mass of electron. You are knowing here the velocity of electron given means the particle is being taken is the electron, and it is having mass 9.1 into 10 to the power minus 31 kg. So after putting these all values in the formula itself, we are getting the Broglie wavelength, that is 1.516 into 10 to the power minus 28 meter. So let us proceed further. Now, the concept of a particle and a wave can be understood by a number of points of distinction between them. So let us discuss the distinction between particle and a wave. So you are knowing particle occupies a well-defined position in the space. That is, a particle is localized in space. Example, a grain of sand, a cricket ball, etc. But on the other hand, for wave, it is spread out in space. For example, on throwing a stone in a pond of water, the waves start moving out in the form of concentric circles. Similarly, if the sound of the speaker reaches everybody in the audience, thus a wave is delocalized in space. So this is the first one, localized. A particle is localized in space and a wave is delocalized in space. Now coming towards the second difference, that is when a particular space is occupied by one particle, the same space cannot be occupied simultaneously by another particle. In other words, we can say that particles do not interfere. It's a simple thing. On the other hand, two or more waves can coexist in the same region of space and hence interfere. Later on, we will learn about superposition of waves in physics. Now, coming towards the third difference, that is when a number of particles are present in a given region of space, their total value is equal to their sum. That is, it is neither less nor more. And on the other hand, for wave, when a number of waves are present in a given region of space, due to interference, the resultant wave can be larger or smaller than the individual waves. That is, interference may be constructive or destructive. So I hope it's clear to you all now what difference between particle and wave. So let us proceed further towards the differences between matter waves and electromagnetic waves. Matter waves, how matter waves are different from electromagnetic waves, though both of them are different in various aspects. So let us discuss some of them. So first one, you are knowing that what are electromagnetic waves. First of all, those are waves are associated with electric and magnetic fields and which are perpendicular to each other and to the direction of propagation. Those are electromagnetic waves. And just now in de Broglie concept, we have discussed what are matter waves. Matter waves are not associated with electric and magnetic fields. Now second one, for electromagnetic waves, they do not require any medium for propagation. They can pass through the vacuum even. And for matter waves, they do require medium for their propagation. They cannot pass through vacuum. Third one, electromagnetic waves travel with the same speed as that of light. And for matter waves, they travel with lower speeds. Moreover, it is not constant for all matter waves. Now fourth one, electromagnetic waves leave the source. That is, they are emitted by the source. And they are having the wavelength lambda is equals to c upon nu. And for matter waves, they do not leave the moving particle. That is, they are not emitted by the particle. And their wavelength, we can write it as de Broglie wavelength. That is, lambda is equals to h upon mv. So I hope it's a simple differences between both of them. So I hope it's clear to all of you. So let us proceed further towards our next topic, that is Heisenberg uncertainty principle and its significance as well. So later on, students, many experiments were done for the verification of the dual characters of electrons as well. The Wisher German experiment were done for the wave character, and some other experiments were also done for the particle character, for proving the particle character of the electron. So now after that, Heisenberg uncertainty principle. Now what this principle tell us? So let us discuss. As all of you are knowing that all moving objects that we see around us, example a car, a planet, a ball thrown in the air, etc., move along with a definite paths or in a definite trajectories, we can say. So hence their position and velocity can be measured accurately at any instant of time. However, such an accurate measurement is not possible for subatomic particles. So therefore, the existence of definite paths or trajectories for subatomic particles is ruled out. So as a consequence of dual nature of matter, Werner Heisenberg, a German physicist, in 1927 gave a principle about the uncertainties in simultaneous measurements of position and momentum of small particles. It is known as Heisenberg uncertainty principle. And the statement is like this. He stated that it is impossible to measure simultaneously the position and momentum of a small particle with absolute accuracy or certainty. If an attempt is made to measure any one of these two quantities with higher accuracy, the other becomes less accurate. The product of the uncertainty in the position and the uncertainty in the momentum. Position del x and for momentum del p, that is equals to m del v, where m is the mass and del v is the uncertainty in velocity, is always constant, and it is equals to or greater than h upon 2 pi, and where you are knowing h is Planck's constant. So thus we can write it as del x into del p will be greater than or equals to h upon 4 pi. However, for most of the purposes, suppose in numerical problems, the mathematical expression for the Heisenberg uncertainty principle is simply written as del x into del p will be equals to h upon 4 pi. So keeping in view of the above expression 1, the value of del p calculated for a given value of del x using the expression second one, the last one, del x into del p. So we are knowing that similarly we can say the value of del x can be calculated for a given value of del p, and that will be minimum value of del x. So now we are knowing that del p is equals to n m into del v. So we can simply substitute here del p. If we are going to substitute here the del p value, what we are going to get? Del x into m del v will be greater than or equals to h upon 4 pi. Or simply if we want to write, we can simply write del x into del v will be greater than or equals to h upon 4 pi m. I hope you have understood. It's a simple thing. So this simply implies that the position and velocity of a particle cannot be measured simultaneously with certainty. It is important to understand that uncertainty principle applies to position and momentum along the same axis. Thus, if del x is along x-axis, then del p should also be along x-axis. It is further important to remember that the uncertainty principle is not an account of any limitation of the measuring instrument. Suppose we attempt to measure both the position and momentum of an electron. And to pinpoint the position of the electron, we have to use light, so that the photon of the light strikes the electron and the reflected photon is seen in the microscope. As a result of the hitting, the position as well as the velocity of the electron are disturbed. So according to principle of optics, we can say that the accuracy with which the position of a particle can be measured depends upon the wavelength of the light used. Thus, the uncertainty's position is plus minus of lambda. That is the uncertainty in position, and that depends on the wavelength. Just now I have told you according to the principle of optics. So we can simply say that the shorter the wavelength, the greater will be the accuracy. But shorter wavelength means higher frequency and hence higher energy. So this high energy photon on striking the electron changes its speed as well as direction. So I hope now it's clear to all of you how uncertainty principle is being explained by using the example of, just now I have taken you the example of an electron. Okay, so let us proceed further towards the significance of Heisenberg uncertainty principle. Like the Broglie equation, although Heisenberg uncertainty principle holds good for all objects, but it is significant only for microscopic particles. The reason for this is quite obvious. The energy of the photon is insufficient to change the position and velocity of bigger bodies when it collides with them. So suppose if we are taking example, the light from a torch falling on a running rat, suppose in a dark room. So it neither changes the speed of the rat nor its direction. That is the position. So this may further be explained. Let us take one more example. Suppose for a particle of mass 1 mg, we have del x into del v is equals to h upon 4 pi m. So substituting the values h, value of pi 3.14, value of m, and here m we have just, I have told you 1 milligram. So 1 milligram, that will be, that is 10 to the power minus 6 kg. So if we are going to substitute all of these values in the given formula, then you will get around 10 to the power minus 28 meter square per second. So we can, after getting the product del x into del v, we are getting 10 to the power minus 28. So which is extremely small value. So for the particles of mass greater than 1 mg, the product will still be smaller. But so hence these values are negligible. So we can, because it's a very small value, so we can, these values are negligible. Now suppose if we are considering any microscopic particles, suppose an electron. So we have to use the same formula, del x into del v, that is h upon 4 pi m, substituting the value of h, substituting the value of pi, and substituting the value of m. And here m is the mass of electron, that is 9.1 into 10 to the power minus 31 kg. So after calculating this one here, in this case we are getting 10 to the power minus 4 meter square per second. So we can say that if uncertainty in position is 10 to the power minus 4 meter, uncertainty in velocity will be 1 meter per second, which is quite significant. So it is for this reason only that Bohr's concept of fixed circular path with definite position and momentum of electron have been replaced by stating that electron has the probability of having a given position and momentum. So this forms the basis of quantum or wave mechanical model of atom. As we have to discuss, we will discuss it later on as well. So we can also say that since in everyday life we come across big objects only, so the position and velocity of which can be measured accurately. So Heisenberg uncertainty principle has no significance in everyday life, similar to the Broglie concept. So I hope it's clear to all of you what is the significance of Heisenberg uncertainty principle. It is more significant only for microscopic particles. So let us discuss one question. The question is like this: a golf ball has a mass of 40 gram and a speed of 45 meter per second. If the speed can be measured within accuracy of 2%, calculate the uncertainty in position. So you have to calculate the uncertainty in position, that is del x. So uncertainty speed is equals to 2% of 40 meter per second. So that will, speed means, uncertainty in speed means del v. So del v is equals to 2 divided by 100 into 45. So that we are getting 0.9 meter per second. That is uncertainty in speed. Now again applying the uncertainty principle, we are having the formula del x into del p, that is m into del v, will be equals to h upon 4 pi. So after substituting the values which we have already having, del x will be equals to h upon 4 pi m del v, and we are having the formula, we are having the value of h, pi, m, del v, because m been given to us 40 grams. So in terms of kg we can write 40 into 10 to the power minus 3 kg. So after calculating this one, we are getting the value 1.46 into 10 to the power minus 33 meter. This is the uncertainty in position, that is del x value. So today we have discussed about the Broglie concept of dual nature of matter, including its significance, as well as Heisenberg uncertainty principle, including its significance, and we have also discussed two questions along with the differences between a particle, wave, and differences between electromagnetic waves and matter waves. I hope all of you have understood it well. So thank you, students.